Hello. In this video, we're going to finish talking about some basic notions about infinite series. We're going to take a look at a quick way to decide when an infinite series might diverge. That's the nth term test. And also talk about the geometric series, which will be another very, very important series in our future work. So we've already defined what we mean by the sum of an infinite series, summation k equals 1 to infinity a sub k, defined as follows. That summation is taken to be the limit as n goes to infinity of the sum as k equals 1 to n a sub k. That's a finite sum out to n terms. And we take the limit of that partial sum as n goes to infinity. So as you can see here, we are using the notation still s sub n to denote this sum of the first n terms of the series, and kind of reiterated that down here. Now, a limit may exist or it may not exist. If this limit in 1 exists and is a finite number s, then we're going to say the sum of the infinite series is s, and we'll simply write summation ak equals s. On the other hand, if that limit does not exist or is plus or minus infinity, then in those cases we're going to say that the infinite series diverges. Now, given an infinite series, of course, we just saw how we can calculate the partial sums. Sn equals summation k equals 1 to n a sub k. Moreover, it turns out that if we know the partial sums Sn, that is that sequence S1, comma S2, comma S3, and so forth, then we can find the AKs, that is the terms associated with the series. So in other words, we're going to show now that if we know all the numbers in that sequence, then we can find A1, A2, A3, etc. This really isn't hard to do, just takes a little subtraction. So first of all, A1's pretty easy because A1 is just S1 because S1 is the sum of just the first term of the series. And if you take Sn minus 1 and add a sub n to it, you get Sn. So a sub n is Sn minus 1. And just to see how this works out in an example, let's take a look at S5 minus S4. S5 is the sum A1 through A5. S4 the sum A1 through A4. And if we do that subtraction, we can see that only A5 is left. So again, given the partial sums S1, S2, S3, we then have knowledge of and can find the individual terms A1, A2, A3, etc. Now, let's suppose we have a convergent infinite series. Summation k equals infinity a sub k equals s. So that is the infinite series converges to s. And of course, this means by our definition that if we take the limit of the partial sums as n goes to infinity, we get s. Now, this statement's also true. Both expressions just ask us what happens to the s sub n's when n gets large, and as n goes to infinity in either one of these, we're getting s sub, say, capital N for a really large n. So both of those limits turn out to be s. We're going to use this now by going back to our terms from partial sums formula. So what this means is the following. If we look at a sub n, that's given by Sn minus 1, as we saw in the previous slide. So if we take the limit of these as n goes to infinity, coming over here, again, remember the series is convergent. So each of these limits turns out to be just the sum of the series, and s minus s is 0. So what we get out of this is if the series converges, then the limit of the a sub n is 0. That is, the terms you're adding must be getting very, very small. So summarizing that discussion, we see the following statement. If summation k equals 1 to infinity a sub k equals s, that is, the series converges to a finite real number, then the limit as k goes to infinity of a sub k is equal to 0. In other words, if an infinite series converges, then the limit of the sequence of terms of the infinite series must be 0. And we can look at an example here to kind of verify that. In an earlier video, we looked at a telescoping series, summation k equals 1 to infinity 1 over k times k plus 1, and we noted that that series, in fact, converged to 1. Okay, it's a convergent series, And of course, as a consequence of this rule up here, that means if I take the limit of the terms, I better get 0. Well, look what happens here. A sub k is 1 over k times k plus 1. And sure enough, as we take the limit as k goes to infinity, that turns out to be 0, as it must, because we've already verified that that statement is true. Now, you want to be careful with this result. It's easy to misuse it, so please pay attention to the following. It turns out that if the limit as k goes to infinity, a sub k is equal to 0, and we're going to run across a lot of series for which that is true, then based only on that information, you cannot conclude that the series converges. In fact, more work is needed to determine convergence or divergence of an infinite series in this case. So again, just because you know that the limit of the terms is 0, you cannot say that this infinite series converges. That's a different statement than the one we just looked at, that if the series converges, then the terms go to 0, but the opposite statement, if the terms go to 0, then the series converges, is not true. We can see an example of this in a previous video. We looked at the harmonic series, which we defined to be the sums of the reciprocals of the positive integers, sum k equals 1 to infinity, 1 over k. We showed that that series diverges to plus infinity. Notice, though, that if you take the limit of the AKs, that limit is 0, and so even though the terms are going to 0, the series still diverges. So again, you want to be very, very careful not to misuse this result. It is frequently misused by students as they start to learn this subject. Now, there's another way to express this nth term test. We've already seen the first way. In other words, if an infinite series converges, then the terms must go to 0 in the limit. However, we can state the contrapositive here, which says the following. And this is going to be much more useful for us. The contrapositive statement says this: if the limit as k goes to infinity, the AKs is not 0, then the infinite series diverges. So think about this a moment. We already know that if this series converges, then the terms must go to 0. So that means if the terms are not going to 0 in the limit, then the series diverges. And not going to 0 means this limit might be some non-zero number, or it could just not exist. So this is a test we will use. This is often referred to as the nth term divergence test. That's what I like to call it anyway. It is a quick way to identify some divergent series. If the things you're adding up are not going to 0, that are not getting small, then the infinite series summation k to infinity a sub k must diverge. So here's an example. In an earlier video, we worked with the infinite series summation k equals 1 to infinity minus 1 to the k. And we saw if we write this series out, it just becomes minus 1 plus 1 minus 1 plus 1 minus 1, etc. And this alternation in sign just continues. Okay. Now for this series, it's easy to see that if you take the limit as k goes to infinity a sub k, that is a limit of minus 1 to the k. This particular sequence bounces back and forth between minus 1 and 1. Never settles down, therefore it diverges. The limit does not exist. And because that limit is not 0, that's all that's important, we conclude the infinite series diverges. So we showed this in an earlier video, though, by working with the partial sums, but this one also, we can get the divergence very quickly by using this nth term divergence test. We're now going to move on to the second part of this video, that is the study of the geometric series. Geometric series is defined as follows. There's two parameters we're concerned with. There's a number a that's not equal to 0 generally, and a number r. These are both fixed real numbers. The geometric series with first term a and ratio r is defined to be summation k equals 0 to infinity a times r to the k. And this just writes out to a plus ar squared plus ar cubed, etc. So this is called a geometric series. Learn this form. You're going to see them a lot. and it's important you be able to identify geometric series in the various forms they might appear. For example, look at this infinite series. It's the summation k equals 2 to infinity of minus 2/3 to the k. And if you write that out, it becomes 2 plus 2 times minus 2/3 plus 2 times minus 2/3 squared, etc. And the generic or general term 2 times minus 2/3 to the k. So in this geometric series, the first term, first one you write down, is 2, and the ratio, that is the quantity by which subsequent terms are multiplied, you multiply by 2 minus 2/3 to go from the first term to the second, then again multiplied by minus 2/3 to go from the second term to the third, etc. So the ratio here is minus 2/3. This infinite series, summation k equals 2 to infinity, 3/2 to the k. Now notice here we've started at the number 2. So our series starts with k equals 2. So our first term is the k equals 2 term. So this is a geometric series with first term 2 times 3/2 squared. And again, notice that we have the ratio 3/2. To go from the first term to the second, we just multiply by 3/2. To go from the second term to the third, multiply by 3/2 again, and that's what builds the powers of 3/2. So watch for this difference in the starting point for the series. Once you write it out and identify this common ratio from term to term, you'll know the first term, the first term of the series is just the one you write down first, and the ratio should be pretty easy to identify. In the remainder of this video, we're going to answer some questions. For a not equal to 0, for what values of r does the geometric series converge? We're not going to talk about the a equals 0 case, but you should think about that. Of course, if a is 0, every term in the infinite series is 0, and so the series converges to 0. I'm going to say no more about that, though. Okay, first, as far as our convergence question, let's look at the case when r is bigger than or equal to 1 or less than or equal to minus 1. So remember, we're looking at the infinite series, the geometric series summation a r to the k. K equals maybe, well, we'll go with 0 to infinity, and that's a plus ar squared, etc. So we're going to apply our nth term divergence test to this series by noting that if the r is bigger than 1 and a is not 0, then this limit is going to be plus or minus infinity, which is certainly not 0. And in the case where r is less than minus 1, this limit of the terms does not exist. If r is less than or equal to minus 1, you'll find that this thing bounces back and forth between positive and negative numbers, but they're not getting close to 0. So this is an easy analysis for this series. If the r is bigger than or equal to 1 in absolute value, then the series diverges. So there's a conclusion there. Then by the nth term test, the geometric series diverges. And so anytime we have a geometric series, notice the r is bigger than or equal to 1 in absolute value, we know that it diverges. Now, what if r is strictly between minus 1 and 1? We can find the sum of the series then by taking the limit of the sequence of partial sums. Again, often finding partial sums is very difficult or impossible, but with the geometric series, we'll see it's quite easy. During this discussion, we're going to use the following fact that if I take a number between minus 1 and 1, strictly between minus 1 and 1, and raise it to a large power, then the result is small numbers. In other words, limit as n goes to infinity of r to the n equals 0 if minus 1 less than r less than 1. So let's take a look at the nth partial sum of the geometric series in this case. So S sub n then is the summation as k runs from 0 to n of ar to the k. And if we write this out, it just looks like this. A plus ar squared plus ar cubed until we get down to ar to the nth, the last term. We're going to multiply both sides of this expression by r. And then the result is in this new line you see here. So r times Sn gives rsn. And if I multiply the right side here by r and then distribute the r inside. The a times r gives the AR times r gives AR squared, etc. So we've taken the results of the product of each term and just moved them a little bit to the right to get them under the similar term above. Notice near the end, the AR to the n minus 1 will multiply by r to get AR to the n, and AR to the n will give AR to the n plus 1. This term will come from something before it right there. So we see a lot of similarities between the terms in these two lines, and for that reason we're going to subtract the lower equation of the upper equation and see the result. So if we subtract RSN from SN, we get SN minus RSN. And on the right-hand side, if we subtract the lower from the upper, the ARs cancel, the AR squareds cancel, etc. Everything cancels. We're left with only the A and this subtracted term AR to the n minus 1. And so that accounts for the right-hand side of the equation. So a lot of cancellation here, and we get a very simple expression. So now it's easy to solve for Sn. Just divide both sides by 1 minus r, and we have the partial sums of the geometric series displayed right there. Now we haven't yet used the fact that r is between minus 1 and 1, so in fact this formula for the partial sums is true for all values of r. As long as r is not equal to 1, then there's some special considerations. But now we're going to recall that r is supposed to be between minus 1 and 1 and take the limit to get the sum of the series. So by definition of the sum of an infinite series, we have for r strictly between minus 1 and 1, the sum of the series is the limit as n goes to infinity of the partial sum, summation k equals 0 to n a r to the k, and that's the limit as n goes to infinity of Sn. Again, we've just called this thing by its compact name Sn. We just figured out that Sn is given by a minus ar to the n plus 1 over 1 minus r. So we've just put the Sn we found in the previous work right here. Now take the limit as n goes to infinity. The only place n occurs is in this exponent, so we can take this limit by moving the limit inside and focusing it on this term, the only term that has the n in it. And again, remember, because r is between minus 1 and 1 and not equal to minus 1 or 1, that limit turns out to be 0. And so we get a over 1 minus r. So we saw how telescoping series can sum very easily. Their partial sums easy to evaluate, then we can evaluate the limit to determine the convergence or divergence. Likewise with geometric series, the partial sums are not that hard to determine, and we can use the definition of sum of a series then to see the sum of the geometric series in the case that it converges. So summarizing, we have the following, that if a is not 0, then a plus ar squared plus ar cubed, etc., that is geometric series, diverges if the S value of r is bigger than 1, and it converges to a over 1 minus r, provided minus 1 less than r less than 1. We're going to use this a lot, so please commit it to memory and think about how you're going to recognize geometric series when they occur in some different forms. We'll finish with a couple of examples to see what these things might look like. So as a first example, let's discuss the infinite series, summation k equals 0 to infinity, 2 times the quantity minus 2/3 to the k. So we write out the series so we can see a little better what's going on. K starts at 0, and so when k is 0, the minus 2/3 to the k becomes 1, so our first term is just 2, then 2 times minus 2/3, 2 times minus 2/3 squared, etc. So we can identify the first term, a as we call it, is 2, and the ratio is minus 2/3. And because minus 2/3 is strictly between minus 1 and 1, we know that this geometric series converges. We've already derived a formula for the sum of such a series, so we're going to go back and use that formula, that this series then must converge to a over 1 minus r. The a was 2, the r was minus 2/3, and this arithmetic gives us 6/5. Another example, let's look at something a bit more complex. Let's find all values of x for which the infinite series summation k equals 2 to infinity, 3x minus 8, quantity all raised to the kth power, divided by 5 converges. Then we're going to find the sum of the series for such x. Let's start off by writing out the infinite series. Now, in this case, the k starts at 2, so the first term happens when k equals 2. That gives us this term. So this is going to be our a, our first term, and then we write out the subsequent terms. As we go from one term to the next, we multiply by 3x minus 8, and so we see those powers growing down here as you move out in the series. So this infinite series has first term 3x minus 8 squared over 5, and the ratio is 3x minus 8. Once we've identified the ratio in the first term, we go back and ask what does it take for a geometric series to converge. We know it converges only for those x for which the absolute value of r, in this case that's our 3x minus 8, is less than 1. So we want to know when the series converges. These are the only x's for which it converges, x's that make that r in the absolute value less than 1. So we solve this inequality. Absolute value 3x minus 8 less than 1 means 3x minus 8 itself is between minus 1 and 1. If I add 8 to all three sides of this inequality and then divide by 3, we find that we must have x between 7/3 and 3 and not equal to either of those two endpoints. So those are the x's for which the infinite series converges. Now, assuming we have such an x, then we can sum the series. So again, here's the geometric series we're looking at. And here's the first term, there's the a. And of course, the ratio, again, is 3x minus 8. And we're going to assume the x is between 7/3 and 3 so that the r is less than 1 in absolute value. And in that case, the infinite series sums to a over 1 minus r. The first term a we identified as 3x minus 8 squared over 5. The r is 3x minus 8. And then just a little bit of algebra. We see the sum of that series is 3x minus 8 squared over 45 minus 15x, provided x is strictly between 7/3 and 3. Okay, the takeaways here. We studied two different aspects about series. The first is the nth term test, which says the following. This is the way we're going to use it. Let summation k equals 1 to infinity a sub k be an infinite series. And if the limit of a sub k, as k equals infinity, is not 0, so this means it might be a non-zero finite number, it might be plus or minus infinity, or it simply might not exist for other reasons. If any of these things happen, then the infinite series must diverge. This is a great test to know, great fact to know, because when you identify such a series and note that the terms aren't going to 0, you can just dispense with it right away, say it diverges, move on to the next problem. Again, be very, very careful. If the limit as k goes to infinity a sub k equals 0, this is not enough to tell you the infinite series converges. You're going to have to do more work beyond just this knowledge. We studied the geometric series. That's a series of the form summation k equals 0 to infinity a r to the kth power. Should have had an exponent of k up here. And that goes a plus ar squared plus ar cubed, etc. This is called the geometric series. And the term a is called the first term of the geometric series. And the expression r is called the ratio of the geometric series. We're going to usually assume that a is not equal to 0, assuming you can take care of the easy a equals 0 case on your own. Now, for a not equal to 0, the geometric series, summation k equals a r to the kth, converges if minus 1 less than r less than 1, and diverges if r is less than or equal to minus 1 or r is greater or equal to 1. So we showed why this latter happens by using the nth term test. So more specifically, again, you want a series like this, and you should be able to conclude very quickly what happens. You'll know it diverges if that common ratio is at least as big as 1 in absolute value. And if that common ratio is strictly between -1 and 1, you can immediately write down the sum of the series as a over 1 minus r. As seen in the last example, though, a and r can take many different forms. We had a equals 3x minus 8 squared over 5, and r was 3x minus 8 in the last example we looked at before getting to the conclusion remarks. So we can use the geometric summation formula then as kind of a template up here, in that, remember, the a and the r may take very, very different forms. And as long as the expression for r is between -1 and 1, that geometric series will converge, and then you're free to use this information up here to talk about the sum and the possible divergence. So 2 very important concepts in this video: the nth term test, which is a great way to tell if a series diverges, and the geometric series. We will see a lot with geometric series in our future work in this chapter.